Welcome back. I am going to talk about a very important topic, so-called regularization in least squares and regression. Before I define the problem, let me overview what we did over the last few lectures. We used the model y hat equals to theta transpose x multiplied by w to represent the relationship between a dependent variable y and an independent variable x. We used standard unweighted least squares to determine w. You can also use the weighted version if some data is more important than others, which we also covered weighted least squares. Anyhow, I would like to focus on the standard least squares problem, right? We basically minimize this cost function, and we have omega. Omega's constructed with S by N matrix. Omega is constructed using these basis functions evaluated at 1 to n data points, and the y here also includes this n 1 to n dependent variables that we have, such that y is an n by 1 vector. So we basically set the gradient of w, the gradient of v, which is dv over dw, to 0, which gives us the analytical solution that we found over the last few lectures for parametric or non-parametric regression, where you can also use a gradient descent to iteratively find the same solution. Now, here we come to a very important practical question. We know that omega transpose is generally non-singular when n is greater or equal to s. But what happens if this is not the case? If you cannot invert it, which if it is non-singular you cannot invert it, then you cannot find the solution. So at this point, regularization solves this problem once and for all. So that's why this is one of the very important topics in practice. So let's introduce the regularization process. All right, in the regularization process, we introduce additional weight to the cost function that we are going to minimize. Here is the lambda to the norm of this w. And lambda is a positive constant, it's a scalar. So when you take the gradient of v, dv, or when you take the partial derivative with respect to w, you arrive, from the first term you have this, from the second term, right, you have lambda w transpose w. So this portion is equivalent to the cost function that you have. So to take the partial derivative, I am going to look at the matrix cookbook, and in the matrix cookbook we have this formula. When you take partial derivative of this function with respect to z, you have this one. This is particularly useful when you take the first term's partial derivative. And the first term's partial derivative by using this formula is 1 over n omega in parentheses y minus omega transpose w. The second term is just, its partial derivative is 2 lambda w. So you have this in here. So now we computed delta v. If you want to find the analytical solution, you set dv to 0, because we know minimum occurs when this dv equals to delta v equals to 0. So from here, when you set it to 0, you can get rid of 1 over n's, and you can write it like this. Now you can expand the first term, you can write it like that, and then you can group for w and solve for w. You are going to arrive w equals to omega transpose plus lambda I inverse omega y. Now let's think a case that it is singular. If it is singular, we know that 0 is an eigenvalue of this omega transpose. So once you introduce this term, we know that since this is positive, you are shifting that zero eigenvalue to the positive region, meaning that you are going to create a non-singular matrix. So in this case, a unique W always exists. So that's the that makes this regularization process a very powerful process that you can find a solution to this least squares problem. As this being said, for a reason that I am going to cover in the next example, lambda shouldn't be so large because it will make a mess of, it will make not a great fit. We are going to cover that. Now you can also use gradient descent solution. We discussed the advantages of gradient descent when you deal with online data in the previous videos. So basically, wk plus 1 equals to wk plus minus alpha positive multiplied by delta v, and delta v is here. If you go ahead and plug it in here, you are going to arrive A and B matrices. This structure, this is a discrete time system. A has this form and B has this form. As always, make sure the eigenvalues of A are inside the unit circle before implementation, because if they are inside the unit circle, then your convergence will be guaranteed. All right, so let's look at an MATLAB example. I will start with 20 data points. I select an independent variable and I select a function. In practice, you don't have that function, but for simulation purposes, I generated some dependent variable. I will start with lambda 0. I highlighted n equals to 20 and lambda equals to 0. I have 11 radial basis functions and one bias. So basically S is 12 and initial number of data points is 20. I am going to reduce this number of points from 20 to something less than 12, such that omega transpose won't be invertible, and going to show you the power of the regularization process by assigning some positive value to lambda. The rest of the code is pretty similar to the previous codes. Basically, this is for the evaluation of the fit, and then this is for plotting purposes. You can stop the video and code it yourself. I always suggest to code by yourself to get a feeling of what's going on here. Okay, this is the first result. Basically, when you have 20 number of points and lambda equals to 0, you basically have a great fit. So now what's going on is when I reduce the number of data points to 10 and lambda is 0, I got this warning from the MATLAB saying that matrix is close to singular or badly scaled. Actually, then you have this interesting overfitting issues here and there. Well, once you assign lambda to be 0.01 for the same number of data points, look how beautiful this fit is. We basically make a very nice fit to this data only by choosing lambda to be 0.01, so small value, and it makes a great fit. Let's look at a more drastic case. Remember, we have 12 as our S, the dimension of the theta. Now we reduced n to 6. We have insufficient number of data points. And when we try to fit with lambda equals to 0, we had a huge overfitting issue. And if you zoom it here, actually, you are not going to get a great fit. But once you introduce lambda to be 0.01, when you do the regularization process in least squares, you are going to have a beautiful fit to these 6 points. This is my final slide. I'm going to look at the case when n is 20. N is 20. So when you can also use lambda to be 0.01 for the 20 data points. It won't change much your fit, still a perfect fit. But if you increase lambda and if you keep increasing more and more, you are going to see that your fit is no longer fitting. So to make the long story short, regularization is a very powerful process, and simply by selecting lambda some sufficiently small value, I used here 0.01, you can prevents singularity, you can have the solution. But do not increase lambda much, because if you increase lambda to an 110, your fit, the solution, or the solution of this regression will not look good. And with this plot, I just wanted to demonstrate that. All right, take care.